Okay, so 7.6, we talk about masses, we talk about moments of inertia, centroids. So let's take a minute and look at center of mass and moment. So if you think about torque, what torque is, the way you calculate torque is force times distance. So imagine that you have a wrench and you're putting a wrench on this and you just can't get it to turn. Then what do? You put a longer wrench on it. And what happens there is if you're exerting the same force here or the same force here, if you have a longer arm, then that creates a higher torque. So even if you have the same force applied, if your distance increases, that increases how much torque, and that torque causes a rotation. So force is mass times acceleration. Um, Sometimes that acceleration is due to gravity. Moment of inertia, or a moment, um, is calculated basically the same way, but instead of considering it a force, we're taking gravity out of the picture and we're just dealing with the mass times the distance. Or you could say the radius, and that radius is just the distance from a certain point to where that mass is located. So let's suppose that we have this diagram above here, and we want to locate the center of mass. Imagine that we have a long beam, and that beam has no mass, and we want to find out where would we need to put a fulcrum so that this balances. You can think of it as a seesaw. Where would we need to put the middle of the seesaw so that with these masses, they balance each other out? So if this is the center, if we put this mass, if this was the only mass on there, it would cause it to rotate this way. So with this one. But if everything else was off and this was the only mass, it would rotate that way. And this one would do the same. So we want to find out if we add all of our moments together. So if we sum our moments, when is that going to be in what's known as equilibrium? When is it going to be still? So we need to calculate the moment for each one of these masses and add them together. We're going to consider a clockwise rotation to be a positive moment and a counterclockwise rotation to be a negative moment. So if we have this in the correct location, the moment caused from these two masses is going to cancel out the moment caused from those, so there's not going to be any rotation happening. So we go back and look. Let's call this x position x sub 0. This would be x1, x2, x3, and x4. So this distance, sometimes we refer to that as the moment arm, is this x value minus this x value. And if this is causing a positive rotation, we want that distance to be considered positive. So for mass 3, its radius, or its moment arm, is x3 minus x sub 0. For this one, its moment is mass 4 times this x minus x sub 0. Notice, just think about x values. If this x location is 3 and this x location is 1, 3 minus 1 is a positive number. So a positive radius times a positive mass, that would cause a positive rotation. Same thing here. If this x value is 7 and that's 1, 7 minus 1 is a positive radius times a positive mass, that makes a positive rotation. On the other hand, if this is to the left, if we do x2 minus x sub 0, when we subtract those, that's actually going to come out to be a negative number. A negative number times that mass, negative times positive is negative, so that creates a negative moment. And the same thing with the one out front. So when we add those together, we want our total moment to come out to be 0. So if we multiply this out, we get m1x1. Let me see, I'm going to go ahead and move some things over. So m1x1, m2x2, m3x3, m4x4. All of the m1, all the m times x zeros, those are negative, so let's move those to the other side. So we would have m1x0 plus m2x0, m3, m4. From the right side, we can factor out the x sub zeros. If we factor out the x sub zeros, we would just have mass 1 plus 2 all the way to 4. So we would just have the total mass times x sub 0. On the other side, we just had the sum of the moments. We could call that sum of mi xi's as I goes from 1 to 4. So if we want to find out what x sub 0, what the location needs to be so that we're in equilibrium, we would divide by the total mass. So our x sub 0, sometimes that's referred to as x bar. That's the sum of the moments over the total mass. So let's work at an example. Oops. Here. So let's suppose we have, let's draw some circles. Let's say we have a circle here, and then a little circle here. So let's say this mass is 2 grams, and this mass is 4 grams, and this mass is 12 grams. So let's make a prediction of where we anticipate our fulcrum to be. We need some x values, so let's call this x value x equals 1 here. Let's say this is at 6, and this x value is at 9. So I'm just going to anticipate where I expect the fulcrum to be. I may anticipate it's going to be here, and I'm going to call that x sub 0. But it doesn't really matter on our diagram. We might anticipate it's here, but it might be on the other side. But we just have to do our formula. So we want to sum our moments. So it's the mass here times this x. So 2 times 1. The mass here times its x. The mass here times its x. So we have 2 plus 24 plus 108. So that's 110. So it's at 134. And then our total mass, we have 2 grams there, plus 4 grams there, plus 12 grams there. So we have a total of 18 grams for our mass. So our location, our balance point, would be the sum of the moments over 18. So 134 to, oops, not 13. 134 divided by 18, about 7.4. So that would be the x value where our balance point would occur. So just sum the moments, sum the masses, and do the moments divided by the masses. Now that's in one dimension. I think in homework there's one where it asks you for the x and the y value. If all of that's in the x, then we can assume that the y value there is 0. So our balance point would be 7.4, and in the y direction we're not up or down any. So let's do one where we're in 2 dimensions. So let me put this here. Let's put a mass here, a mass here, and a mass here. So imagine somehow these were all stabilized together by some massless connectors. And we want to find out, where would our balance point be? Where would the center of mass be? So let's just estimate it to be somewhere in this area. X bar, Y bar. So we just have something in 2 dimensions. We need to find out left and right, where would the center of mass be? And then up and down, where would the center of mass be? So X bar, we do the same way we did before. We sum the masses times the xi values over the total mass. In the y direction, we sum the moment in the y direction, the mass times the y value over the total mass. Now, sometimes you'll see this referred to as the moment about the y-axis. Now, if this is x, why is that called y? Well, if we're looking in the x direction, this distance, this is the x distance to that point. This is the x distance to that point. X is measured from the y-axis. And same thing here. This x is measured from the y-axis. So this is saying the moment measured from the y-axis. You could also think about this would, if we didn't have these others, if we pushed here, it would cause it to rotate around this y-axis. Same thing here. This is considered the moment measured from the x-axis. So if this was 10 grams and this is 8 grams and this is 6 grams, then if we want to find the center in the x direction, then we sum the moments in the x direction. So I'm just going to go left to right. So the mass here times its x component plus the mass here times its x component plus this mass times its x. So we get negative 40 plus 12 plus 56. So let's see, that's 16 plus 12 is 28. If we take the moment about the x-axis, we do the MIYIs. So I'm just going to go bottom to top. So it's this mass times its y value plus this mass times its y value plus this top mass times its y value. So 10 plus 32 plus 42. So that's 42 plus 42 is 84. We need the total mass. So 10 plus 6 plus 8. That's 16, so 24. So our x bar, the x component of the center of mass, is 28 over the total mass, and the y component is 84 over the total mass. So that's 1 and 4/24, 1 and 1/6. Let's see, if we reduce this, if we do 84 divided by 24, that's 72, 12, so that's what, 3.5? 84 divided by 24 is 3.5. So our center of mass is over 1 and 1/6 up 3.5. Over 1 and 1/6 up 3.5. So we were pretty close. that's where our center of mass will be located. So if you imagine, let's say we had a weightless piece of cardboard and we had these masses at each of the vertices, then our balance point where we could put our finger at and it not rotate would be here. So that's just extending what we did on the first problem to 2 dimensions. But in each of these problems, we had a finite or a specific number of points. We didn't have an unlimited number of masses, or we didn't have a continuous area. So that's really not per se a calculus problem there. But let's suppose we have some function here and some function here. Let's call this f and let's call this g. And we go from A to B. And we want to find out where is the center of mass, or where is the centroid here. Okay, so let's take a sample element here. And this area that we have, it has a density. And this, we're going to use this letter rho to represent our density. And this is going to be a laminar density. We have the same density throughout the whole area. So it's not a variable density. And instead of our density being volume per mass, it's going to be, or mass per unit volume, it's going to be mass per unit area, because this is a 2-dimensional problem. So let's start out by how would we find the mass of our sample element, which has a thickness dx? Well, if we rearrange that equation, mass is just the density times the area. Well, how do we get the area of that box? Well, it's the height times the width. The height of that is the top y minus the bottom y, and the width of it is dx. So if we want the total area of that whole region, we integrate that from left to right, and then we multiply it times the density, and that'll give us the total mass of our area there. So if we want to find the center of mass, we're going to do a couple things. One thing is we're going to say for our sample element, the center of mass is located in the middle. If the density is consistent from one end to the other, think about having like a meter stick or a yardstick. If you put your finger right in the middle, it's going to be balanced because you have the same amount of weight on each end. That y value, if it's in the middle, how do you get halfway between two numbers? Well, the easiest way is to average them. Add those two numbers together and divide by 2. And that'll give you the middle. So let's begin by finding, let's say, the moment on the y-axis, and then we'll come back and we'll do the moment measured from the x-axis. Actually, let's do the x first. So the moment from the x-axis, if we imagine putting all of our weight is actually distributed, but to make the problem simpler, we consider that all of our mass is located at that one point. So if we're summing our masses times our radius, then our radius is the distance from there to there, which is that y value, and we call that f plus g over 2. The mass, we said, comes from this formula. So make my equal sign over. The mass is f minus g. The integral of that times dx, and then we multiply that times the density. So That part is the mass. That part is the radius, or the moment arm. So mass and the moment arm. To get the moment measured from the y-axis, this is the moment arm. Well, that is just what is our current x value. So the moment from the y-axis, again, we sum the mass times the radius from the y-axis, or we could call this y and this x. So that moment arm is given by x. The mass is still F minus G dx. Let me erase this to make room. The mass is still F minus G dx integrated from A to B times rho. So this part, and that part, that's the mass. This part is the moment arm. So all of those up got to give us the moment from the y-axis. So y an integral just means add them up. So we have this sample element, we have this sample element, we have this sample element. We take each of our elements, we find the moment at each one of those. So F minus G times x dx times rho. This adds them together, and that gives us the moment from the y-axis. Here, the moment arm is F plus G over 2. The mass is given by that. So when we combine those two, F plus G over 2 times the mass, that gives us how much, what the moment is from the x-axis. We add those up for every little sample element. So then, to get x and y, the center of mass, and that's the moment from the y-axis, that's the x location over the total mass, and the moment from the x-axis, the y value, divided by the total mass. So I'm going to do that by example. So here's an example. We have this region, y equals the square root of x, which is like a sideways parabola. Y equals 0, which is the x-axis, and x equals 4. So there's our region. We want to find the centroid, the center of mass of there. So here's our sample element. We're going to call this F. We're going to call this G. So let's get the mass. So that's our density times the integral. Our sample element on these are going to be dx. So it's the top F. F is the square root of x minus the bottom, well, the bottom is always at 0. And we're going from left to right, so from 0 to 4. We're not told specifically for this one what the density is. We may or may not have to know that. We'll see that in just a little bit. Square root of x, we could call that x to the 1/2. So when we integrate that, that's x to the 1 bigger power over that power, or we could say times the reciprocal, evaluated from 0 to 4. So the 3/2 over 3/2 are times 2/3. So if we put in 4, we have 2/3 times a rho. If we put a 4 in, the square root of 4 is 2, to the 3rd power is 8. If we put a 0 in, 0 to any power is 0. So our total mass of that whole area is 2 times 8, so 16 times rho over 3. So if you were to tell me the density of that region, I could tell you the mass. All right, now let's get the moment from the x-axis. So that's rho times the integral from 0 to 4 of f minus g, so square root of x minus 0, times f plus g, square root of x plus 0, over 2 dx. So remember the moment from the x-axis, that's f minus g times f plus g over 2. That's what we integrate. In this case, remember f is the square root of x, g, y equals 0. So this minus that, this plus that. Simplify this. Square root times square root cancel, leaving us an x. 2 is a constant. We can pull that out front. We're integrating that from 0 to 4. So if we integrate that, we get x squared over 2. We still have our rho over 2 out front, and we're evaluating that from 0 to 4. So we get 4 on bottom, and evaluate that from 0 to 4. So 4 squared, that's 16 over 4. And when we put a 0 in, we get 0. So 4 rho is the moment measured from the x-axis. Now we need the moment measured from the y. So that's rho times the integral of f minus g times x dx, and we're going from 0 to 4. So we can remember that one's rho a to b f minus g times x dx. So the square root of x times x, this is x to the 1/2, this is x to the first, so that's x to the 3/2. So when we integrate that, that's x to the 1 bigger power over that power, evaluated from 0 to 4. So we have 2/5 times rho out front. If we put a 4 in, the square root of 4 is 2. 2 to the 5th is 32. So if we multiply that, we get 64 rho over 5. So that's the moment about the y-axis. Center, we take the moment from the y over the total mass, the moment from the x over the total mass. So the moment from the y-axis is 64 rho over 5, and then our total mass was 16 rho over 3. The moment from the total mass was 16 rho over 3. So if we simplify that, that'll give us our center. Simplify that, let's do 64 rho over 5. Multiply times the reciprocal. So the densities cancel out. So notice we didn't even have to know the density here. We just had to know it was a constant. 16 goes into 64 4 times, so we get 12 over 5. So that's our x bar. For the other one, we have 4 rho on top. If we multiply by the reciprocal, our rows cancel. 4 goes into 16 4 times. So our y bar, that comes out to be 3 over 4. That's our center. 12/5, 3/4, or we could call that 2.4 by 0.75. So if we look at our picture, let's grab this. x-axis, and then how far over do we go? We go x equals 4. So that's our area. Our center, oops, our center is over 2.4. So about